Okay, so hello everyone. Let's try to start. As you might remember, last time I said that we are going to quickly finish with complex numbers. Unfortunately, I've done it very slow and finally start vector spaces. So I said we have one more problem. Unfortunately, I was wrong. We really need to discuss two more problems on complex numbers, but still, well, let's go. So one of them is a very interesting one. We have a so-called rational function, basically a fraction where each numerator and denominator are polynomials. Polynomial divided by polynomial. And we want to split it into something more simple. In fact, such a function can be split into a sum of functions of the following type. Some constant divided by x minus some constant plus another one, etc. Such fractions are called primitive fractions. They are much more simple because their power is not the fourth power in the denominator, but linear. Okay. That's my goal, to split this into a sum of the following type summands. So the way how to do it starts with the following. We need to find the roots of the corresponding polynomial. Luckily, we have already discussed this particular polynomial. Those are the brackets that it splits into. Then there is some theoretic fact that we will not prove, but we will simply use that there exist four constants such that this equals this. So the main theoretic part is to know which exactly things to put into the denominators. And the answer is that you need to find the roots of the original polynomial and split it into the corresponding brackets. And then they are in the denominators. Then what remains is to find four numbers, C1, C2, C3, C4. How to do that? We know two approaches. Anyone? No?
Well, logically, no, wait. But because, for example, if we take under the same denominator and multiply all the nominators by corresponding parts, we will get probably equality, like 1 equals, but I'm not sure that. Or maybe it will be easy to solve, but I'm not really sure.
Yeah, okay. So there are kind of two different approaches. One approach is to put four different values of x into the left-hand side and to the right-hand side. Put four values of x, and then we get a system. If you put four different values of x into the left-hand side and right-hand side, in both cases, you get some number here multiplied by C1, number multiplied by C2, etc. So you get a system of four linear equations with four variables. However, the equations will be hard. Well, maybe not really hard, but there will be four of them with four variables and the coefficients won't be nice. So there is another way. Indeed, we can put, multiply by the common denominator, that is by this number by the product of those four by this polynomial, product of those four polynomials, then in the left hand side we get 1, or whatever was in the nominator originally, and in the right hand side I get the following. Okay, I won't rewrite the last two, but it is easy to understand how they should look like. And again, there are two ways to solve this. One way is to open the brackets and compare the coefficients. Indeed, here you will have some coefficient before x cubed, for example. It will be c1 times x cubed plus c2 times x cubed, etc. So if this, and on the left-hand side here, you have no x cubed, then it follows that c1 plus c2 plus c3 plus c4 equals 0. And likewise, you have some equation for x squared and for x and for the, well, the free term. And for the free term, it will be not 0 on the other side, but 1. However, this equation looks nice, but the other three won't look nice. So again, this method is doable, but quite hard. I wish to do it another way. But before I go here, is this part understandable? What we could do by brute force?
Yeah.
No questions yet? Then let me go fast. So the really nice way is to now put particular numbers into this equation. For some reason, it was bad to do before, but good to do now. And the reason is that now I can pick better values of x that were forbidden last time. For x equals 1 plus I, we get 1 equals c1 times 1 plus I minus 1 plus I times 1 plus I plus 1 plus I times whatever. 1 plus I plus 1 minus I plus c2 multiplied by 0 by something plus c3 multiplied by something by 0 by something, and plus c4 multiplied by, again, lots of somethings, but with 0. That's because this bracket x minus 1 minus I appears here, here, and here. This bracket, it was in the first denominator, so now it appears for the other three fractions in the nominator after we multiplied. Thus, this part vanishes, and we get that c1 equals 1 divided by this, this, and this. And all that remains is a problem of a simple computation. But I don't need to solve systems. This system has solved itself. C1 is like separate from other three. And the same way for x2 equals 1 minus I, etc., etc., etc. I can find C2, C3, C4. Questions? Fine. Sorry. Now, also x4 plus 4 equals x squared minus a 2x plus 2 times x squared plus 2x plus 2, as we learned last time. And thus, it is also possible to do the following, to rewrite it as, maybe let me name that not c, because they are not equal to those numbers, but like d1 plus d2x over this plus d3 plus d4x over this, where these are real numbers. Everything here is real. So the idea is that over real numbers, sometimes you can't split a quadratic polynomial into two brackets. So such things, they're also called primitive fractions over R. Primitive fractions over R. Over complex numbers, only linear things can be in the denominator, and here something non-linear, something quadratic maybe. Still, it's easy to find such a splitting. Again, you can do it by brute force. You simply will take the this expression and think that I don't know d1, d2, d3, d4. Let's find them by any way, like by putting 4 values of x or by multiplying everything by this. Either way, it will work. But the easiest way is to first solve the previous problem, then take them as pairs. Like those roots are complex conjugate to each other, and those roots are complex conjugate to each other. So I claim that if you add those two fractions together, you will obtain exactly this expression, or this one, I'm not sure which is which, but one of those two expressions, and the denominator will automatically become real without any work. Automatically. That's it. Are you sure there are no questions? Okay. I see that everyone is overwhelmed with complex numbers. So one final question. I'm sorry, that's the previous question. But one final question that still is also quite relevant. Okay. Sorry, my mouse doesn't want to copy. So the last talk I want to talk about is this. So suppose I have some polynomial that, well, has roots by the main theorem of algebra. However, I don't know how to find them. You can try to find the roots for this and you won't succeed. So they exist, but we don't have any formula, any way to like somehow use them. Still, there is a task to find their sum. We can't find those numbers, but we somehow want to find the sum of those numbers. A very strange situation. Well, in fact, it is still possible to do so. And the thing that enables us to do this is called Vieta's formulas. The idea is as follows. If there are 5 roots, again, I don't know them, but I can write that my original polynomial equals this expression. Then I can mentally open the brackets in this expression. What will I will obtain the following: z to the 5th power minus z with different coefficients times z to the 4th power plus something by z cubed minus something, etc. So we can see by comparing this term to this term that Z1 plus Z2 plus etc. plus Z5 equals 1. This coefficient equals this coefficient minus, the sum is minus 1. Is it clear?
Yes.
You should have studied in school the particular case of Vieta's formulas for n equals 2 when the polynomial is quadratic. This is a generalization. For any power, in fact, there exists such a set of formulas. They're called Vieta's formulas. Maybe formulae for pedantic people. That's the proper plural, but everyone says formulas. Well, what if, for example, I had the following polynomial? What would be the sum?
One and a half.
1.5, 3 over 2, because in this would be split as 2 times the product of something, something, something. And so this coefficient would be 2 times the sum. So this 3 is 2 times the sum. So we need to divide. The general rule is that for Vieta's formulas, you always divide by the main term so that your polynomial has the same roots, but the main term becomes just 1. This polynomial is kind of equivalent to this one. I mean, their roots are the same, but for this one, it is easier to understand the Vieta's formulas. Okay, very good. The final question is how to find this sum. And the idea is as follows. Let me return to this product and examine not only this term, but the next one. The next one looks as follows. I can pick coefficients in 2 brackets and z cubed from 3 other brackets. I'm sorry, this will take a bit of time.
And how did we get this coefficient for z cubed?
Let me finish it. So again, if you look at this product, there are 5 brackets. You can pick, to get z cubed, you need to pick z from 3 brackets. Then you get 1z, 2z, 3z, z cubed. But then from 2 other brackets, you pick numbers, minus z1, for example, and minus z5. When you multiply them, minuses cancel, you get a plus. Here in the previous one, it was a minus because there was 1 number. Here it is a plus because there are 2 numbers. And the numbers themselves are multiplied. And each way of doing this gives me another and another and another sum. Okay?
Okay.
So this huge expression gives me another Vieta's formula. That this sum equals the coefficient before z cubed. In my particular polynomial, it is 0. I forgot my polynomial, but it could be not 0, but some other number depending on the polynomial. That doesn't really matter. What matters is that now I can solve my problem because the sum of squares is the, well, the square of the sum minus twice this awful expression. In our particular case, that's 1 squared minus 2 times 0, that's 1. But again, the particular case doesn't really matter. What matters is the general case. We are able to do this for any situation. There are many more problems of this type, but I think I have to stop at some point, so let it be this. When the preparation lists for the exam go out, you will see one more problem of this type there. And I hope now everyone will be able to solve it. And if not, we will have a consultation before the exam. Okay, no questions yet? Then let's finally go to the new topic. I'm sorry that we are slightly, well, behind the lectures still. As I already said, we're going to be able to catch up at some point. So vector spaces. I really hope everyone read the lecture notes and listened to the lecture, etc., because this is a, well, not very, well, a quite easy concept, but it requires some time to understand it. And most of things that are hard are not practical, but theoretical. So the main thing at this point for, well, the next month or something is not the seminar, but the lecture. I really hope everyone understands the theory. Still, the idea, I remind you, is as follows. We have some fixed field f. It will usually be real numbers simply. You can always, when it is hard to think about some fields, you can simply think, okay, numbers. It won't be a problem for most of our tasks. So you have some field and you have some set of objects. So this set V is called a vector space if there are two operations: addition that takes two vectors, two elements of V, and produces another one, and multiplication by a constant. It takes an element of V and a number and produces another element of V. And there are some properties that need to be satisfied, and there are many of them. I won't write them down, but you have them in the lecture notes. The idea, so why are we interested in such, well, thing? Well, the idea is that we have many different things that satisfy well, those rules. So one example is the set of columns. If you have the set of all possible columns like this for all possible A1, etc., AN, then this set we denote with the symbol R to the nth power. Okay, and this set, well, is quite useful. We will use it the entire year a lot, and it is easy to see that it satisfies those rules. If you have several columns, you can add them and you get a column, And if you have a number, you can multiply a column by a number. And you get still a column of the same size. And again, there are some properties that need to be checked. I'm sure that in the lecture, this example was checked. And so basically, all the properties follow from the properties for matrices. Second example is geometric vectors. Geometric vectors on Euclidean plane. We know from school some concept of vectors, and well, they also can be added to each other, and they can be multiplied by a number. So they also satisfy those prerequisites, and there are some properties again that could be checked, and well, I won't go into details, but they are true for geometric vectors. So they are another example, and in fact those examples kind of look related to each other in some sense, and they are, and we're going to go into more details well next time. Are there any questions yet?
So the plane differs from the Descartes' plane, yeah?
What do you mean? Евклидова плоскость.
Да, плоскость. Она отличается чем-то от Декартовой системы? Ну, имеется в виду то, что мы ее же используем в построении векторов или нет?
I don't understand the question. So,
okay.
I mean, you can have Cartesian coordinates on a Euclidean plane. Yes, that's okay. And in fact, using coordinates, you can explain how geometric vectors simply, okay, maybe I shouldn't have drawn the coordinate axis. Simply on a plane, you have vectors like the geometric definition, okay? A vector is such a segment with direction where if two segments are something, then we call them the same vector, okay? And then for vectors, you can find coordinates and you will come to something like this. We will discuss this procedure, how from one way of expressing things go to another way of expressing things next time.
Okay.
And the notion of coordinates. What is coordinates? But right now, let me produce several more examples. Matrices. If you have some fixed numbers n and m, then rectangular matrices of fixed size, you can add them together. If they're of the same size, then you can add them without problems, and you can multiply them by a number. So they also form a vector space. Again, there are some properties to be checked, but in case of matrices, they're also satisfied. And again, I will skip this. Polynomials. Okay, this example is kind of not related to the previous ones, right? Still, it is a good example. If you have two polynomials, f and g, you can add them together. The result will be a polynomial. And also, if you have a polynomial f, you can multiply it by a number. You will get another polynomial. So again, there are some properties that should be checked, and it is more or less easy to do it if you understand what is a polynomial, and you will see that they are satisfied. So this is yet another example. We will often use in problems not the space of all polynomials, because it is kind of hard to work with it, but the space of bounded polynomials. For example, like this. This is the set of all polynomials with power 3 or less. like this. Okay, polynomials with degree 3 or less. Okay, lecturer prefers to write them like this. I usually try to use his notation, but this is the situation where I won't. This notation is horrible and I'm against it. So I'm sorry for confusing it, but I will continue to write it like this. Okay. So, but in all the problems, it will usually be said what this notation means. So don't worry too much. Finally, I wanted to have one final example before I go on. Functions. For example, from real line to real line, the functions you study in calculus, any functions, well, you can add functions point-wise. At each point, the sum of functions gives the sum. And you can multiply a function by a number. Or if you wish, continuous functions. This is a different set. Again, those two are different because there exists some non-continuous function. But continuous functions from R to R, they also form a vector space because when you add them or multiply by a number, you still get a continuous function. Okay, this is some set of examples. So the idea is that there are many different things that work the same way. They satisfy the same set of rules. So if we prove some theorems that say for any vector space something, 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 then such theorems can be used for geometric vectors, for polynomials, for matrices, for functions separately. This is the main idea of algebra, proving some general theorems that you can then go and use in different particular cases. So I hope I have explained why we have to suffer, why we have to discuss vector spaces, at least partially explained. Now let's go to some, well, more practical problems. And before we do that, let me have, okay. Here are some questions for you now. Consider the set of all matrices, of all square matrices, such that their determinant equals 1. Okay, we take all matrices n by n whose determinant is 1. Is this a vector space or not? This is a question for you. It's not hard.
I guess no.
Why?
Because if we sum these matrices, we will get to the other field.
Other field?
Other vector space.
Other vector space?
Like the determinant won't be equal to
We
1.
will get outside of this set, right? For example, if n equals 2, but it is easier to generalize this example for any n, then the sum doesn't have determinant 1, the sum of such. So this set is not closed under addition. When you add elements of this set, you get something not from this set. So the operation of addition is not well defined on this set. plus is not well defined on this. Okay, because the result is not inside but outside. Any questions? This is an important example. What can happen when something is not a vector space?
Can you repeat what is SL?
What is SL? Again, this is simply a notation. I didn't really explain it, but this set we are talking about, and it is denoted by those letters for some reason. Okay. This again, you don't need to memorize those letters yet. We will return to them in several months. But this is simply a letter to denote this set. This set is set of all matrices with determinant equals 1. Okay. Well, let me try another set. It doesn't have any standard notation, so let me just write some letter. Also in matrices, but with determinant 0. Maybe 0 is better. No one? Feel free to talk. Don't hesitate.
So is it possible to do you consider for example, adding a matrix 3 by 3 and add to matrix 2 by 2 or no?
No. N is fixed.
It's fixed. Okay. Then it is a field, I suppose.
Not a field.
Not a field, but vector space.
Why?
Because if we are considering, for example, adding, it will be true always.
Why?
No, I'm wrong. Yeah.
Yes or no?
Yeah, because for example, if we are taking 2 by 2 matrix with 1, yeah, you can just write 1 0 0 0 and 0 0 0 1. So it will be determined 1 event. So
very good. This is again a popular counterexample. You can add determinants with matrices with determinant 0 and get something with determinant non-zero. Basically, the idea of those two exercises is that, well, determinants have nothing to do with addition of matrices, okay? Adding matrices and determinants are, well, like from different topics, they don't mix together well. So determinants are very interesting things, but unfortunately, they have nothing to do with vector spaces. We can't form a vector space by such a nice rule, unfortunately. So this is also not a vector space. Okay, one more example. I will already use, let me use Z. So the space of all polynomials such that f of -5 equals 0. We take not all polynomials, but only those who have -5 as their root.
It's a vector space, I guess.
Why?
Because if we multiply these two polynomials, we will get 0 multiplied by 0. And...
Okay, that's true, but not what we need to check, because in vector spaces we do not consider multiplying different vectors. Some of our examples, give me a moment then to talk about this. So in some of our examples, like in matrices and in polynomials and in functions, there is an additional operation of multiplying them. But right now we ignore it. We like don't look at it. We are not going to multiply those objects, well, for quite a long time. Okay. I mean, when we are thinking about them as vectors, then we don't multiply them. Okay. Because we want to prove like some things that are general, that are that work for all of those examples, not only for those that have some additional properties. Okay, so let me return here. Please continue.
If we'll sum them, then we'll get 0 plus 0.
Indeed, if there are two polynomials f and g and both are 0 at this point, then f plus g at this point, by definition of f plus g, is f at this point plus g at this point, which is 0 plus 0, which is 0. So automatically, their sum is 0 at this point. Likewise, obviously, if I multiply the polynomial by a constant, then at every point, the value of the polynomial gets multiplied by this constant. But if I multiply 0 by a constant, I get 0. So this set is closed under those two operations. Those two operations are well defined. So Z is closed under those operations, or in other terms, the same thing in different words. Those operations are well defined on Z. In Russian that is замкнуто относительно этих операций. Let me even write it, in fact. Замкнуто относительно. And this is корректно определены. Эти операции корректно определены на Z. Можно сказать, корректно заданы. Вообще просто корректны. So, well, this is not the end. There is also a list of axioms of vector space that need to be checked. But it is very, very boring to check them. Lucky for us, there is a shortcut. The shortcut is as follows. We know that Z is a subset of the set of polynomials. You are studying set theory right now in discrete mathematics, right?
Yes.
Okay, so subset is not a problem. So Z is a subset of R of X, part of R of X. And for any elements of R of X, all those silly axioms are true. For example, for any f1 and f2, f1 plus f2 equals f2 plus f1, okay, for example. But then it automatically follows that for f1 and f2 from Z, also f1 plus f2 equals f2 plus f1. So we get a powerful rule. If our like candidate into vector spaces is a subset of something that we already know to be a vector space, and the operations are the same, then we need to check whether it is well defined, whether the operations are well defined on Z. But if we check that, we do not need to check the axioms. All of them are automatically satisfied. And in such situation, Z is called a subspace of the bigger space, subspace of R of X in this case. So a subspace, again, is a subset that is a vector space itself, a good subset. Let me give more examples of subspaces. Consider the set of columns where those 4 numbers are arbitrary, but this number is 0. This is a subset of R5 of the set of all columns with any 5 numbers in the column. I claim this is not only a subset, but a subspace. Indeed, when you add 2 columns of this sort, then the result is easy to write, and it also has 0 in this cell. So it also belongs, let me name it, I don't know, W. So if you take 2 elements from W and add them, you also get an element of W. And the same for multiplication by a constant. So W is a subspace of R5. At this point, it might be logical to ask how to denote, how to write down that something is a subspace of something. I can write it down as well as a sentence like this, but maybe it would be helpful to have some notation, right? Some symbol for this. Who remembers from the lectures maybe what kind of a symbol we have?
Square brackets? No.
No.
It is the nothing.
No. Well, the situation is horrible, but the symbol is this. So this wonderful symbol, its meaning depends on context. We have lots of things whose meaning depends on context. That's one more of them. For any sets in any kind of mathematics, this means that something on the left, so for sets, means A is a subset of B. But when B is a vector space, we also write A is like lies in B with different meaning. A is a subspace of B. So in this sense, writing like this was a mistake, because at this point I didn't check it yet. So but after we checked, this became correct. It is indeed a subspace. So in linear algebra, this sign will mean not subset, but subspace. That's, again, that's life. The idea why we use the same sign with different meaning is basically because we will never need to use subsets, well, almost never, but we will often need to use subspaces. That's again, a historical problem. Maybe it would be better if they had two different signs, but that's life. People have not invented two different signs for some reason. Okay, any questions here? Okay, then let me give another example. Consider a Euclidean plane. Again, maybe let me not draw any coordinates, but no, let me draw coordinates. Still, consider the Euclidean plane and consider some line passing through the origin like this. Okay, primaya, a line. Then let me consider several vectors lying in this line. Okay, in fact, all of them. The set of vectors lying in this line. Then when I add two of them, their sum also lies in the same line. You can see it like evidently. You can look at the picture. And if you multiply such a vector by a number, it has the same direction, so it also lies in the same line. So this is a subspace of this space of all vectors on the plane. Okay, any questions for this example? Okay, let me.
So sorry, is that like red line is a subspace?
Yes. So the set of all vectors on this red line is a subspace of the set of all vectors.
Okay.
Let me maybe give a final example before we move to the next topic. Symmetric matrices. Consider matrices n times n square matrices, and among them there are symmetric matrices. Well, if two matrices are symmetric, then their sum is also symmetric. Sorry. If A equals A transposed and B equals B transposed, then A plus B equals A plus B transposed. And if A equals A transposed, then lambda A equals lambda A transposed. So if this means that the operations are well defined on this set, so this set is a subspace of this. Symmetric matrices also form a vector space. Any questions for this example? Okay. Now, this ends the part about talking generally about spaces and subspaces. Now, let me finally state a huge goal of the next several seminars. The goal is to find a method how to transform a problem about any vector space V. Well, any, not really, but almost any. We will just, again, when we discuss the method, we will discuss which vector spaces. Still, about any vector space V to a problem about Rn, about columns of coordinates. That's our goal. We're going to do some preparatory things today and next time. And after that, we will obtain a method how instead of solving some things about functions or polynomials or matrices or geometric pictures, to replace any such problem with a problem about columns. And then we will use the language of matrices to work with such problems. That's exactly the main goal of linear algebra and the reason why matrices were invented. They are a language which allows to solve problems about any vector spaces by somehow transforming the problem into problem about easy vector spaces. That's, again, the idea of the entire part of the course. I wanted to state it explicitly so you understand what we are like approaching, what is the direction we're going. Okay? Okay, this was kind of philosophical, so no questions. Okay, now we have 20 minutes with something, so let's go on. By the way, a good moment to mention that next time there might be a surprise quiz on complex numbers. That's life. Okay, no one is surprised yet. You shall be. So one final topic I hope to talk about today is linear combinations. So, well, the concept itself is very easy. Suppose I have several vectors in some vector space. When people have elements of a vector space, sometimes we put a bar above those elements. The goal of this is to not mix them with numbers, to distinguish them, to be able to differentiate them. I mean, well, yeah. So that they are written differently, not like numbers. But this is not absolute. Sometimes people don't write this bar. It depends on the context. Sometimes you want to write it and sometimes you don't. It depends on, well, how much of confusion could be if you don't write it. Okay? In books, also people sometimes write bold letters, жирные буквы. Instead of this bar, they use a bold letter. Okay? Okay. So suppose there are several vectors. And suppose there are several numbers. Sorry. In our field. Again, my field is going to be R for most of the cases. So I will simply write R. Then I can multiply each vector by its own number. And the result is called a linear combination of V1, etc., Vs with coefficients alpha 1, etc., alpha s. That's it. Nothing really new here. We have been using linear combinations for like many times already. We simply have a new name for them. Nothing really changed. This is the simple operation of multiply one thing by a number plus multiply another thing by a number plus etc. Like V1 plus V2 is a linear combination. The coefficients are 1 and 1, or V1 minus V3, or 2V1 plus square root of 2V2, etc. Okay, all of those are linear combinations. Please note that some of the coefficients might be 0. Sometimes we can write them explicitly. For example, I can write like this. Or sometimes we omit them like this. We don't write zeros. That depends again on our choice. We are free to do this. But still, zeros can exist among the coefficients. So if all combinations, if all alphas are 0, then, well, we get a stupid linear combination. But mathematicians don't like the word stupid. So instead, they say trivial linear combination. This situation is called trivial linear combination. And so we have come to the definition from the lecture, which we are going to work with in the remaining 20 minutes. So a set of vectors are called, well, not are, but a set of vectors is called, that's better, linearly dependent. Please note that linearly independent, you should consider them to be one word, okay? They can't be separated. This is one term. It has a particular meaning, okay? It is expressed through two words, but it is one term. So it is there. This set is called linearly dependent if there exists a non-trivial combination, linear combination, alpha 1 v1 plus etc. plus alpha s vs, such that the result is still 0. So if you are able to somehow cancel your vectors with each other, then they're linearly dependent with each other. Otherwise, we say that they are independent. So finally, we come to some, well, particular problems. So let us go through the following two examples. Well, when there are two examples, it is obvious that the answer in one is, well, the one way and in the other way, but still let us work through them diligently. So the first one, I have three vectors, v1, v2, v3, which are rows of numbers. Usually, well, again, for some historical reasons, usually we're going to use columns, not rows, okay? But it doesn't really matter much. And in some textbooks, they use instead rows, not columns. I have taken this from some textbook and they use rows, okay? Also, they put commas. In matrices, we usually don't put commas between cells, but here there are commas, okay? That doesn't really matter. Still, what this means is that we have three matrices, this matrix, and this matrix as a set. And the question is, are they linearly dependent or independent? So they ask whether there exist such numbers alpha 1, alpha 2, and alpha 3 such that this combination equals 0, 0, 0, the zero vector in this space. Well, how to find whether those alphas exist or not? It's obvious. We have to simplify the left-hand side. If you really do the operations, it becomes 2 alpha 1 plus 3 alpha 2 plus alpha 3. the first cell. The second cell becomes -3 alpha1 minus alpha2 minus 4 alpha3. The last becomes alpha1 plus 5 alpha2 plus 3 alpha3. And so this equals 0, 0, 0. But if two matrices are equal, then each cell is equal. So we obtain the following system of equations. Okay. Now I have to solve it. And there are two possibilities. Either it has solutions or it doesn't have solutions. And I'm interested in two possibilities. Do those alphas exist or not? So let me do it quickly. If I add those two rows to the middle row, some things cancel and some things don't. This cancels and this cancels, but this doesn't. I get 8 minus 1, that's 7. So I can divide it by 7 and subtract from two other rows. Okay. Now, well, it's easy to finish. It's kind of obvious that the result, what will be the result, because this minor now 2113 is obviously non-degenerate. It is non-zero. So I will do several operations, but in the result, I will get this. So what does this matrix tell me? It tells me that the system is equivalent to the system alpha1 equals 0, alpha2 equals 0, alpha3 equals 0. Which means that the solution, well, exists, but only one solution, the trivial solution. This system is homogeneous. It has zeros on the right-hand side. So it always has the solution 0, 0, 0. No matter what are the coefficients in the left-hand side, still 0, 0, 0 will suffice. But in the definition, we said that we are interested if there exists some other solution, not this one, but anything else. And here it doesn't. No other solution exists. So non-trivial linear combination that gives 0 doesn't exist. So the set V1, V2, V3 is linearly independent. Questions? Was it easy?
Sorry, can I have only one question?
Mm-hmm.
I just didn't get why when we multiplied alpha2 on the brackets, everything got minuses.
Sorry.
Like we have here -3 alpha, minus alpha. Here, yes.
So -3 times alpha1 is the second here in the second cell, here in the second cell, -1 and here.
Mm-hmm.
Well, it's randomly, all three coefficients were with minuses. That's just some random example.
Yes, I got it. Thank you.
Mm-hmm. So if you look carefully at this matrix, so now that we know the method, it makes sense to streamline it, to not do many additional steps. The steps here in this part were like us thinking about how to check. So now that we know those steps, we can go immediately from the original vectors to this matrix. The rule is as follows. You take your vectors that are given here, this, and this, and no matter are they rows or columns, you write them as columns into your system. Then you solve it and check whether there are non-trivial solutions or not. This system, again, always has solution 0, 0, 0, but sometimes it has more solutions. Sometimes it doesn't. I'm sorry. Let me use this method on the part B of the task. So I have here 4 vectors in a 4-dimensional space. So my method is as follows. I take them and write as columns. Then I transform this matrix. Unfortunately, this will take some time. I remember there was some clever trick. But I don't remember which one.
We should subtract from first and the fourth column, third column, just by this coefficients. Like from the first one, third one by coefficient 2, and fourth one, yeah. From fourth one, third one.
No. And this one I will divide by 3.
No, okay.
Even better, I won't subtract. I will first divide by 3. And then I will subtract this one from the other ones. So at this moment, in fact, I can stop doing computations. I have a 0 row, thus, no matter what I get in the result, how many non-zero rows, still it is obvious that the number of non-zero rows will be 3 or less. So there are no more than 3 main variables. Thus, there is at least 1 free variable. Okay. It is. Automatically, it follows from this system. So it means that this 1 free variable means that there are some solutions, that solutions exist. There are non-trivial solutions. And if I'm only interested in dependence or independence, then I can say automatically that my original set is linearly dependent. Of course, if someone asks me to find an example of a dependence, an example of particular alphas, such that the combination becomes 0, then I have to find a solution. I have to finish computing and find a particular set of numbers. And that's it. Any questions here? Okay. Then, unfortunately, we have only 4 minutes left. I have one more problem, but we won't be able to do it in 4 minutes. So I think we should just skip it. Next time, we will talk about material of the last lecture and maybe some material from the next, which didn't happen yet. I hope we will catch up. So we will talk mostly about bases, special kinds of independent vectors that are very good and interesting. Okay, if there are no questions right now, then let's finish at this point.
Can you give the link for this desk?
Sure.
And also, can you please send the recording?
The problem is, again, I don't have the recordings. The recordings are in study office. I have written them at some point and we had some discussion and I think we didn't understand each other. So maybe I will write them again, but right now I don't have them. I'm sorry. I will try to write them again. I'm sorry. Maybe that's my fault because I didn't talk with them enough. I don't think.
Okay, thanks.
But right now, unfortunately, I don't have them. And when I have them, it will take time to upload all of them. So right now it is a small problem. I'm sorry.
Okay, thank you for the lecture.
Thank you for the lecture.
Thank you.
It's not a like. Okay.
For the seminar.
Yeah,
Yes.
yeah,
For the seminar.
okay. See you
Yeah,
in a
thank
week.
you. Have a good week.
And I remind you about a surprise quiz.
On the next seminar,
Who knows, but it might happen on the next
Ah.
seminar suddenly. So
surprise
be
quiz. Okay,
surprised.
okay.
Okay.